You can review content from Crash Course Organic Chemistry with the Crash Course app, available now for Android and iOS devices.
Hi, I'm Deboki Chakravarti, and welcome to our last episode of Crash Course Organic Chemistry. Early one morning in 1926, the silent film sensation Rudolph Valentino died at the age of 31. People packed the streets to pay their respects to the actor nicknamed the Latin Lover. Picture 1920s Manhattan with 100,000 distraught fans crowding the streets and 100 horseback police officers. It was quite a dramatic scene. Valentino's untimely death was caused by perforated ulcers, breaks in the stomach lining that didn't heal. But today, we don't need to worry as much about an early demise from ulcers because of the medicines we have to treat them, like proton pump inhibitors. The proton pump inhibitor is inactive until it hits acidic stomach cells, where it undergoes an incredible chemical transformation. The activated drug permanently stops some of the proton pumps that secrete stomach acid. This type of permanent deactivation helps ulcers heal, and it can also help us fight bacterial infections, a main cause of stomach ulcers. In this episode, we'll find out how this kind of chemical inhibition works as we wrap up our Penicillin V synthesis and this series. Pathogens are microorganisms that can cause us harm, like bacteria or viruses. And when medicinal chemists design chemical compounds to treat infections, they can take advantage of the differences between humans and pathogens. Both human cells and single-celled bacteria have cell membranes, but bacteria also have a cell wall to protect them from changes in their environment. The cell wall is a peptidoglycan, a mesh of polysaccharides, that's the glycan part, which are linked up by short chains of amino acids, or peptides. A bacterial enzyme called a transpeptidase cross-links the peptide chains, giving the cell wall its strength. Transpeptidase enzymes have a serine amino acid side chain in the active site, where the cross-linking reaction takes place. And some have a lysine nearby that may help the serine react. Bringing these side chains close together affects both of their chemical properties. The partial negative charge on the lysine's basic amine can tug on the hydrogen of the serine's hydroxyl group, so they're kind of sharing that proton. Specifically, this interaction makes the hydroxyl group more acidic, so it's easier for the serine to lose its proton, which makes it more nucleophilic. To begin the cross-linking reaction, the reactants have to enter the transpeptidase active site. In this case, the peptide part of the peptidoglycan sticks in. Once the peptidoglycan is in place, this extra nucleophilic serine attacks the peptide bond between the two specific amino acids of the peptidoglycan, and lysine can now fully accept serine's proton. This forms a tetrahedral intermediate, and then part of the chain breaks off. Serine forms a temporary covalent bond to the peptide, making an ester. Now, another peptidoglycan, one that's going to be cross-linked to the first, can come into the active site. The amine group of a glycine at the end of the chain reacts with this enzyme-bound ester, reforming a new amide bond, this time with the cross-linking chain. Now the two chains are cross-linked, forming the functional bacterial cell wall. Once an enzyme does its reaction, it returns to the form it started in, with the products released from the active site and the protons where they started. This way, the enzyme can catalyze another reaction. And this is where penicillin can stop the transpeptidase enzyme in its tracks. The 3D structure of penicillin is pretty similar to the amino acids of the peptidoglycans that get cross-linked by transpeptidase. So, penicillin can sneak into the active site. Remember that the beta-lactam ring of penicillin is super reactive, which is why it was so difficult to isolate in the first place. I know we've said that amides are the least reactive of our 4 carboxylic acid derivatives, but the ring strain from the 4-membered ring makes this amide super easy to hydrolyze. Penicillin reacts with the active site serine, again with the help of our nearby lysine. This opens the beta-lactam ring. The active site is blocked by the large penicillin structure, and that's it. Nothing else can happen. The transpeptidase can't cross-link any more cell walls, which weakens them and leaves the bacteria unprotected from its environment. So it bursts and dies. Bye-bye, bacteria. An irreversible inhibitor binds to an enzyme active site, permanently deactivating it. This is what penicillin does to the transpeptidase enzyme, by forming a covalent bond. Here's the 3D structure of a transpeptidase enzyme irreversibly inhibited by penicillin. This is the protein surface, and we can catch a glimpse of penicillin shown as a ball and stick structure in the active site. If we change to the cartoon view of the protein that shows the secondary structure, we can zoom in better and see penicillin clearly. And if we look a little closer, here's the covalent bond to the serine side chain. The 5-membered ring of penicillin is intact, but no more 4-membered beta-lactam ring. The transpeptidase cross-linking is an example of a reaction that forms a peptide bond. In episode 49, we showed amino acids linking up as a straightforward dehydration reaction. But it's actually pretty hard for 2 zwitterionic amino acids to just form a peptide bond. Remember, in a zwitterion, the carboxylic acid is deprotonated and the amine is protonated. Thinking back to episodes 30 through 32, we know that deprotonated carboxylic acids have a resonance-stabilized negative charge. This makes it less likely that nucleophiles will attack. We worked around this by making carboxylic acids into more reactive derivatives, like acid chlorides, anhydrides, or esters. And this is what nature does too. The carboxylic acid on a zwitterionic amino acid is turned into a good leaving group and then hooked onto a carbohydrate on a transfer RNA molecule in an ester linkage. Next, the transfer RNA, transfers the amino acid onto a growing protein chain and helps make that tricky peptide bond. Synthetic chemists have found ways to link amino acids without transfer RNA too. The challenge is getting the order right. Say we want to link up the amino acids alanine and leucine, so the bond forms between the carboxylic acid of alanine and the amine group of leucine. We just learned that living things make the carboxylic acid into an ester, so let's start by doing that. Now, if we mix the ester of our alanine with leucine, we can get the dipeptide we want. But we also might get alanine reacting with another alanine. So it's not enough to just make alanine's carboxylic acid more reactive. We have to prevent alanine's amine group from reacting too. We can do this by slipping on one of the chemical disguises we met in episode 33, a protecting group. Here's our game plan. We'll protect the amine group of alanine with a CBZ group. This temporarily makes the amine into something similar to an amide. So alanine's nitrogen isn't a good nucleophile anymore due to resonance stabilization with the carbonyl. Next, we can use a peptide coupling reagent to turn our carboxylic acid into a better leaving group. 1,3-dicyclohexyl carbodiimide, or DCC, is a classic choice. Then we can toss some leucine into the mix. Leucine's amine group attacks and forms the peptide bond by kicking the ester off the alanine. All that's left to do is remove the protecting group, which comes off easily with hydrogenation conditions. And we've put our amino acids together in the order we want. No transfer RNA required, just some clever synthetic chemistry. Speaking of clever chemistry, let's check out the mechanism of the DCC reaction. The nitrogen of DCC first grabs a proton from the carboxylic acid of alanine, forming a salt. The protonated DCC has resonance stabilization, and this aminium ion is electrophilic at the carbon. Even the weakly nucleophilic carboxylate we just formed on alanine can attack it. This way, when we add leucine, it attacks the alanine in the familiar addition-elimination mechanism of carboxylic acid derivatives. The whole DCC portion of the molecule, along with one of the oxygens from the original carboxylic acid, is the leaving group. A final deprotonation gives us the protected dipeptide, along with the dialkyl urea byproduct. Yes, urea, like the waste product in urine. With that, we've added the final reaction to our toolkit to finish our penicillin synthesis. As our last puzzle, let's break down the mold medicine map and discuss the overall strategy Dr. John C. Sheehan's research team used to synthesize penicillin V. We won't look at every mechanism in detail, since we did that in previous episodes. But we've added those episode numbers to the mold medicine map in case you want to review them. Phase 1 of the synthesis began with valine, which contains the gem dimethyl group needed for the nitrogen and sulfur-containing 5-membered ring. But valine doesn't have a sulfur atom, so they needed to add that. Sulfur is a soft nucleophile and can react with enones through conjugate addition, like we saw in episode 45. So their strategy was to make an enone that sulfur could react with. To begin phase 1, the nitrogen of valine reacted with an acid chloride with a built-in second chloride leaving group. Next, the carboxylic acid was turned into an anhydride, a good leaving group, which let them form a ring. The second chloride was eliminated in an E1Cb reaction, and an isomerization produced the enone. The conjugate addition step added the sulfur and broke the ring back open. Then they hydrolyzed both the ester and amide and made their new sulfur-containing amino acid. This mixture was racemic, so they isolated the enantiomer they wanted in a kinda complex multi-step process we won't get into. Phase 2 of the synthesis prepared a chemical that could introduce the rest of the carbon atoms of the main penicillin chain. But the compound they started with needed one extra carbon atom. With the Claisen condensation, they added that carbon as an aldehyde. This would help them form a ring in the next step. To kick off phase 3, they reacted this aldehyde with the amino acid they made in phase 1. An iminium ion formed, and the sulfur in the same molecule attacked to form the 5-membered ring. Next, they removed the phthalimide protecting group from nitrogen and replaced it with the actual chain of penicillin V. Then they used acid to remove the tert-butyl protecting group from the carboxylic acid. And all they had left to do was form the delicate beta-lactam ring. This ring closure was done using the peptide coupling reagent that we just met, DCC. In fact, DCC will help link up almost any carboxylic acid and amine. They made a salt of one of the carboxylic acids and reacted the other one with DCC. This set up the carboxylic acid for a quick acyl substitution and formed the 4-membered beta-lactam ring. With that, John C. Sheehan's research team completed the first chemical synthesis of penicillin V. It was a lot of steps, and the yields weren't spectacular, so chemists and biologists developed methods to let microorganisms do a lot of the work for us, and make larger quantities of these pathogen-fighting antibiotics. But there's always more work to be done. For example, some bacteria evolve to protect themselves against medicines. In other words, they develop antibiotic resistance. So we keep developing new, better treatments to fight disease. And medicinal chemistry is so much more than just fighting infections. Sometimes our own bodies go a little haywire, and a carefully crafted medicine can help fix all sorts of things, like relieving the pain of a sprained ankle, lowering dangerously high blood pressure, helping us manage depression, healing ulcers, and so much more. All these big questions can be solved with what we've been learning throughout this series. Understanding the properties of organic compounds, making and breaking chemical bonds, and using lab equipment to purify the compounds we want. I know I've said it before, but organic chemistry is everywhere. At the very least, I hope this series has helped you understand the chemical complexities of life a little deeper. So many reactions are going on right under our noses and inside of them. And if you were inspired by these puzzles, know that you can help shape the future of medicine, create better plastics in less polluting ways, and unravel the mysteries of life itself. In this episode, we learned that penicillin fights bacteria by inhibiting an enzyme, explored how proteins are made in the body and in the lab, examined the first full chemical synthesis of penicillin V, and saw, once again, how organic chemistry can help us better understand ourselves and improve our world. Thanks for watching this final episode of Crash Course Organic Chemistry. If you want to help keep all Crash Course free for everybody forever, you can join our community on Patreon.